Okay, I think I'm going to start. No, I'm going to start by going over the course information again, because yesterday I didn't have this sheet. Okay, so it's MAM2084S, linear algebra differential equations. So I'm Thomas Mbewu, and the other lecturer is Thomas van Heerden. He's the convener, so he's the right person to talk to you about admin and stuff. My office is M316 in the Mass building, and his is M101.6 in the Mass building. There aren't any consultation times set yet, so you should you can come and see us, or if you want to make sure that we're there, you can email us to set a time. This is his email, thomas.vanheerden@uc.ac.za, and my email is tmbo@gmail.com. And you can also email to ask maths questions or admin questions or whatever. Okay. Yeah, so lectures Tuesday, Friday here. Men's 10, but also Thomas van Heerden's in M304. The lectures are not compulsory, but the tutorials are very compulsory. You have to go to 11 out of the 12 tutorials. Otherwise, you won't get DP. So if you miss a tutorial for any reason, then you need to, as soon as possible, preferably before, get Thomas van Heerden to accept your excuse. Also to get DP, you also need to get 35% for the class tests, of which there are two. So the first one, 18th September, second, 27th October. And then when you write the exam, that'll count either 80% of your mark or 60% of your mark, whichever gives you the higher grade. The notes for this course, like the textbook, is on Vula. Thomas van Heerden wrote them specifically for this course, so they're really good. And I'm going to follow them, do everything in them. And basically it goes stuff about the fundamentals of vector spaces and linear transformations. And then stuff about determinants. Roughly, a determinant is, you've probably seen determinants before, but you can think of them as a way of just determining the size of a linear transformation or the magnitude of a linear transformation. Then we changed to do differential equations, especially linear ones, because linear algebra can be applied to those to solve them more easily or understand their behavior more easily. And then go back to linear algebra for diagonalization, which is basically a way of turning matrices into nicer matrices, really, that are easier to work with. Or a better way of saying it is it's a good way of choosing a basis for a vector space in terms of the eigenvalues and eigenvectors, but you'll see that later. And then back to differential equations again, Laplace transforms. Laplace transforms are a way of turning a differential equation into an algebraic equation, and then you solve it algebraically, and then you do an inverse Laplace transform to turn it back, and you have your solution. Okay, so that's basically what the course will be. But this is really the first 2 weeks. Linear algebra. Are there any questions about admin type stuff? Or the course in general? Okay, then we can begin. So yesterday yesterday I said that linear algebra is basically about vector spaces, of which there are many, and some of them have particular names, and you have seen them before, and some of them you won't have seen before, and some of them don't really have names because they aren't necessarily used that much, or they're weird. Okay, so that's vector spaces, and we looked at the definition of a vector space. So defining it in terms of it's a certain kind of set with some additional structure. So can anyone remember what the definition of vector space was? Oh, yeah? Okay. Yeah. If I don't notice your hand, then you can totally just talk. Okay. A vector space. So a vector space said is closed under vector addition and closed under scalar multiplication. So a vector space is a set, and let's just give it a name, V. And it's got these two properties, these two extra bits that give it structure of being closed under vector addition. And what does that actually mean? What does it mean to be closed under vector addition? Yeah, when you add two vectors from this set, the resulting vector is also in that set. So it means you take a u and a v in that set, and then when you add them, the result is in that set. Okay. And the other property he mentioned was it's closed under scalar multiplication. And what does that mean? Sorry, someone said it, but I can't. It's like too quiet in here.
So when you dot product a scalar with a vector, you will get just a multiplication of the scalar.
Okay, yeah, but don't call it dot product, because a dot product is specifically when you multiply a way of multiplying two vectors by each other. So, so we call it. So this is one. This is called scalar multiplication, right? So it means if you take a scalar alpha and you take any vector in the vector space and then you scalar multiply the scalar by the vector, you get another vector in the vector space. So you can then go further and you can give the vector space additional structure. You can say, all right, I'm also going to say that there's a dot product, a way of multiplying two vectors by each other. And we're going to look at some of that kind of thing later. Additional structure you can define on the vector space beyond just the simple, but not every vector space is going to have any, not every vector space will have a dot product, will have something that makes sense as a dot product. But every vector space has this structure. Scalar, vector addition, scalar multiplication. Okay. So now I want to look at the other half of this picture. These are the vector spaces, but then you also get linear transformations. So you might get a linear transformation from this vector space to that vector space, from there to there. And it's just it's a kind of map. It's a kind of function from that vector space to that vector space. I'm sure you've seen them before. You've probably seen them before, but I just want to approach them in the way I like to approach them or think of them. So you might have you might have one from there to there, whatever. You might have linear transformation might go from R2 back to R2, and so on and so forth. And now, what I want to say is, I want to define it in terms of the structure. I want the definition of what a linear transformation is to just flow from this definition of what a vector space is. And so I'm going to say that those arrows, a linear transformation, we call it T from vector space V to vector space W, is just a map. Map's another word for function, so a map or a function. You can also call it a transformation, whatever. So it's map, function, and transformation from V to W. And this is the important part, the linear part, that preserves the structure of the vector space. Okay. What does that mean? What do I mean by preserves the structure of the vector space? So you remember when we had, yeah?
Can you just use Y for
Oh, okay, sorry. Shall we write this? Okay, so linear transformation. Which are the blue arrows there? Can you see the blue arrows? Oh, linear transformation is linear transformation T from the one vector space to another is a map or function or transformation from V to W that preserves the vector space structure. Okay, so remember, you can think of a vector space. I think I did this picture yesterday. Yes, I hope I did. Maybe I did. Whatever. Look, there's this. You can think of a vector space as being this set, right? And it's got lots of vectors in it. And okay, so that's just a set with vectors in it, a set with elements. It has no structure. But now you give it a structure. You say, okay, if I add u to v, then I get this particular vector, u plus v. Not that vector, not that vector, not some vector outside the space, but this particular vector. And you also say, oh, it's got the structure of scalar multiplication. So if I multiply this vector by a certain scalar, I'll get, say, this particular vector, not that vector, not that vector, not a vector outside, but that vector inside the vector space. So there's this vector space set with that structure, and a linear transformation is going to map from one vector space to the other. So there's also this vector space. And this vector space also has its structure, that x plus y is that alpha times x is that, or whatever. And so linear transformation goes between them. Okay. So yeah, can anyone say what I mean when I say linear transformation is a map that preserves the structure of the vector space? Yeah?
I think you mean the resulting vector space gives the property of closed, that is closed under addition and scalar multiplication.
Okay, what do you mean by closed? You mean that this vector space is closed under? Okay, so this thing is a vector space, right? So automatically it's closed under vector addition and scalar multiplication. So we don't have to worry about that. So I mean, okay, so it's something like another way of thinking of it is there's some structure in here, right? Like a particular way this is, and when you take these vectors into here, you get like a picture of this vector space in that vector space, and the picture sort of corresponds. It like matches. If this vector plus this vector give you that vector, right? And then suppose your transformation takes that vector to there, takes u to x, and takes that to there. So that means that I'm saying that tu equals x and tv equals y, right? The structure of this is that u and v get added together and give you u plus v, right? So u plus v goes to something. What does it go to? So it goes to tu plus v, goes to something in here. Okay? But if you add the vectors in here, if you add in here tu plus tv, you'll also get some vector, tu plus tv, right? And to preserve the structure is to say, or to preserve the structure of vector addition is to say that it doesn't matter which way around you go. If you add them in here and then take them, it's the same as if you took them individually and then added them in here. So this thing, tu plus tv, is equal to t of u plus v, right? So it's like, here's a picture of, put these two vectors together, get that, and the t takes that picture and turns it into a picture in here that is like an image of the same picture. Take tu, tv, add together, get tu plus v, the same as tu plus tv. So when I say preserve, if I say preserve the vector space structure, that firstly means that it's got to preserve addition, right? That's what that is, preserving addition. It means that when you have two vectors in the vector space, if you add them first, if you add them in V and then transform them, you get the same thing as if you transform them and then add them in W. And I'm sure you've seen this part of the definition of a linear transformation before. And this is how I think of it. It's where does this come from? This just is a natural. This is just the meaning of preserving structure, where structure is vector addition. But there's also some other structure, scalar multiplication, and so we want to preserve that as well, because to be a vector space you have to have scalar multiplication as well, and we define a linear transformation as a transformation that preserves all the vector space structure. So if you take u in here and you multiply by scalar, you get a alpha u. Multiply the scalar alpha, you get alpha u. So if you take u, you'll get tu. So now what happens if you take alpha u, you'll get you'll get t of alpha u, and so what has that got to equal? Yeah, alpha tu. Because you take this tu, you multiply by alpha, and you get that. And that must be the same as if you went u to alpha u and then across there. So in some sense, it preserves. There's this picture of taking u to alpha u, and then that picture is preserved in some way. It can be, in this case, it kind of looks like it's turned upside down, but that's fine. It's changed, but it's preserved in some way. It's like you can see where it comes from. Is the idea? Is the intuitive idea? Okay, so preserves vector space structure. So it means secondly, it preserves scalar multiplication, and that's just that t of alpha u must equal alpha tu. Okay. So this first one was preserves vector addition. And the second one was preserves scalar multiplication. Okay. And so these two things, these two elements, the vector spaces and the linear transformations between them, they are the subject matter of linear algebra, and so these are the most important definitions, really. And everything else about linear algebra really flows from just these definitions. Okay. I want. Can anyone give me like an example of a linear transformation? Y equals 2x. Okay, so what vector space are you thinking of? So it's a linear transformation, so it's got to be from one vector space to another, right? Okay, so you're saying let's take y to 2x. You're saying let's take x to 2x effectively, right? Okay, take x to y, take x to 2x. I think that's what you're saying. So which vector space could this be? Yeah, it could be R. A very simple vector space. And this could be R. Okay, how do you know that that is a linear transformation? Follows rules, you just apply the definition. Okay, so you check if you take t of x1 plus x2, that is 2x1 plus, that is 2 times x1 plus x2, right? Which equals 2 times x1 plus 2 times x2. And if you, on the other hand, if you take t of x1 and you add it to t of x2, you get 2 times x1 plus 2 times x2. And those two things are equal, so it preserves the vector addition. And then the other one, the scalar multiplication, t of alpha x equals 2 times alpha x, and alpha times tx equals alpha times 2x, but these are all just real numbers, so those two things are equal, so it respects the scalar. So that's a simple example of a linear transformation between the vector spaces R and R, which you can also call, if you want, R1 and R1. So now how about the linear transformation? Oh yes, sorry. Mm-hmm. So he said that y equals 2x, right? So it's which is a way of saying that is to say that x gets sent to 2x. So it's like so the function is y equals 2x, right? Which you would maybe draw like that, and x gets sent to 2 times x. So like 1 would be sent to 2, and so on. And so it's like this line, y equals 2x.
So the line of the x1 and x2 will be 2.
Mm-hmm. So I just called, so to check this is true, we have to check what happens when you add two vectors in the vector space, right? Now the vector space in this case is just R1, right? So we need to check what happens when we add two vectors in R1. So what's a vector in R1? It's just a real number. So you have to check what happens when we add two real numbers to each other. So x1 is a real number, x2 is a real number. So I should have said, take x1 in R and x2 in R, right? And then this is true.
So like in the line just for the one that you just written,
Mm-hmm.
we will to say x1 equals to 2x1 and x2 equals to 2x2.
No. Yeah. So this notation means that x gets sent to 2x. So it's y equals 2x is one way of putting it, right? But in this thing, it isn't that. For example, one of the x's is an x might be like 1, for example, and 1 gets sent to 2, and another x is 3, and 3 gets sent to 6, right? Because 2 times 3 is 6. But these x's aren't equal. There's no way in which these x's. This x isn't equal to that. 1 isn't equal to 2. 3 isn't equal to 6. X isn't equal to 2x. It's just that this is a way of saying x gets sent to 2x by the function t. Okay. Maybe it'll be clearer if we look at a more interesting vector space. Oh, yeah.
I don't understand how did you go from y is x1 plus x2 equals to alpha x from the third to last step to the second to last step.
Yeah, I'm sorry, I'm not writing this clearly at all. This is we need to prove these two things. This one and this one, right? The vector addition, scale multiplication. So this is the proof of the vector addition thing, right? So they come to the same thing, they equal each other, so therefore it does preserve that thing is true. Then we move on to the next step. Let's prove the scalar multiplication. Sorry. So we say, okay, take alpha, a scalar. So what is a scalar for R? For the vector space R? Yeah, real number. Scalars are always going to be real numbers, really. Okay, take a scalar, so a real number, and take an x, a vector, which is just also a real number in this case. Okay, and then then you work out what t of alpha x is. The rule defining the function says that x goes to 2x, so that means that alpha x goes to 2 times alpha x. And you also work out what alpha times t of x is. The rule says t of x is 2x. So alpha times 2x. And because these are just real numbers, it doesn't matter what order you add them in. I mean, what order you multiply them in. So they come to the same thing, and so that proves that T alpha x equals alpha tx in this vector space. This proves this, which proves that it's a linear transformation. Okay. So a more interesting vector space would be R2, right? And we might have a transformation from R2 to R2. Okay, so can someone, and that'll take some vector of the form xy, and it will turn it into some t of xy. Okay. Can someone give me an example of a linear transformation from R2 to R2? So something that xy, yeah. Can anyone think of one? Try and maybe write one down and then. Okay, so I'm going to say I assert that this one, send x to 2x, and send xy to the vector 2x, x plus y. Okay, so I'm defining this function as t of xy is equal to first component 2x, second component x plus y. Okay, now I claim that is linear. How are we going to go about proving it? That it is linear, or checking if it's linear. So what should I write here? Well, actually, can you write down for yourself the first proving that it preserves, that this thing does preserve that tradition? Can you try and I'll give you like a minute to try and write that down for yourself, if you can. Does anyone have a good proof, progress on how to do this? Like this? Okay. Okay. Both vectors in the vector space. Okay. Then? Yeah. Perfect. Okay. Now, what is this? What is this thing inside the brackets here? x1, y1 plus x2, y2. What does it work out to? Yeah, that's a rule we know for adding vectors in R2. Add the first component, so x1 plus x2. Add the second component, y1 plus y2. Okay, cool. Now we need to apply this, the way I defined this function. I said that t of xy is 2x, x plus y. So what is this first component here going to be? What is the first component of this going to be? Right. So I take this whole thing, x1 plus x2, that's like the x there, and it's just 2 times that. And the second line is going to be?
x1 plus y1 plus x2 plus y2.
Yeah, but I prefer to say that this is, you take the x first of all, the first component, so x1 plus x2, and then you add it to the y, the second component, which is here y1 plus y2, so y1 plus y2. So you had exactly the same thing, you just changed the order, which is of course you're allowed to do because it's addition. Okay. Oh, sorry, I did that. Okay, so that's what that comes to. Now, next step. Individually, okay. So what is t of x1, y1, and then add that to t of x2, y2, and what do I get? Oh shit. I prefer to do it step by step. So what do I get? I get 2 times x1, and then x1 plus y1, and the next one is 2 times x2 plus y2. Okay? Then if I do this addition, if I add these two here, then I'll get 2x1 plus 2x2, and x1 plus y1 plus x2 plus y2. And those two things are equal, of course, because you can times out the brackets, you can reorder the additions. So that proves that it's preserved vector addition, yeah? So for now, you should think of the power of the R as simply representing the number of elements, the number of rows in the vector. Now that turns out to be the same as the dimension, but we don't yet have a precise definition of what dimension means. So for now, it's an intuitive definition of what dimension means. Oh, I see, yeah. Well, I mean, you can still say, yeah. So all you can say is that if it's 8-dimensional, then it's got 1, 2, 3, 4, 5, 6, 7, 8 rows. That's all we can say. You can't really think of what 8-dimensional space looks like. Okay. So I think I would like to leave the second part of this proof, right, for basically like just do it yourself for homework. But if you struggle with it, show me tomorrow. Come and ask me. Okay, definitely. Because I want to show you this now. So we'd also need to prove scalation, then we'd prove that it's linear. This transformation, right? I could rewrite it like this. I could first of all, I could put all the x's in one vector and all the y's in the other vector. Okay, right? That's the same thing as that. And then I could factorize out the x, and I could factorize out the y. So is it okay? Can you see that that's the same thing as this? That each step of this equality. So now this thing here is it's called a linear combination, which you might know already. It's certain vectors plus certain scalars. Okay? I mean, sorry, it is. So, it's two vectors, each one multiplied by a scalar and then added together. That's a linear combination. A linear combination in this case of two vectors in R2. Now, the thing is, whichever vector xy you give it, right? This thing is saying you always get a linear combination of these two vectors. So it's like if I tell you about this linear transformation, one way to tell you about this linear transformation would be to say it's this linear transformation. It sends xy to that vector. But another way to tell you about it would be to say it sends xy to a linear combination of the vector 2, 1 and 0, 1, where in that linear combination, the coefficients of the linear combination, the scalars in front of the vectors, are the elements of that scalar, of this vector. And it turns out that that is completely general. That the reason it worked for that linear transformation was not because that was specially chosen, but because it works for every linear transformation in R2. So if you have a linear transformation in R2 from R2 to R2, one thing you can definitely say, it turns out, is that it takes the vector x1, x2, let's call it now, and it sends it to t of x1, x2, but that equals x1 times some vector plus x2 times some vector. And let me put it like this. If t from R2 to R2 is a map and is linear, then there are two vectors which are called t11 and t12 and t12, t22, such that that
That over there. This is a second T.
I want to name the rows first, then the columns, just because someone decided it long ago, and it's an irritating thing, but it's whatever. So okay, if T is a linear transformation from R2 to R2, there are always for each linear transformation T, there are these two vectors, such that the linear transformation really is actually just this linear combination like this. Okay, and to save time, we write that we write these things just arranged in a square as a matrix. So you've probably seen this before. We write it like that, and we put the vector x1, x2 over here. And this really is the definition of matrix multiplication in R2 of 2 by 2 matrices. It's that it's an instruction saying to do this linear transformation, take a linear combination of the columns. The columns are going to be the vectors, and these are going to be the scalars. That's why matrix multiplication is defined like it is. And that's why I wanted to name these in this way, because it's traditional in matrices to name the rows first and the columns. And I think to me it seems the wrong way around, but someone decided that a long time ago, and everyone sticks to it. Okay, so this can be generalized, okay, to not just to apply to R2 to R2, but to apply to linear transformations from Rm to Rn. Okay? So now, what does the vector in here look like? Well, actually, let's see. So I want to generalize this. I want to generalize this statement to here. In this one, m was 2 and n was 2, but now they can be anything. Okay, so I'm going to say that if that is linear, then now how many vectors am I going to need to do this, do you think? K, but there's no K. Okay, maybe n vectors. Okay, so then that would be like this. We could call this one T11, and this one T12, all the way to T1n, right? So that would be n. And then now the question is, each of these vectors, how many elements must they have? What do you think? Okay. Okay, let's check that. So this then is saying that these vectors then are in our what? Rm or Rn? Rm, yeah. Okay, is that right? So this linear transformation has got to take. This linear transformation it's got to take a vector in Rm, and it's got to turn it into a vector in Rn, right? And it's going to turn it into that by making a linear transformation of these vectors. Oh, sorry, by making a linear combination of these vectors. So when you do a linear combination, these vectors we put them in Rm, right? And so when we make a linear combination of them, when we multiply each one by a scalar, the result will still be in Rm. And when we add them together, all of them together, the result will still be in Rm. So we'll end up with something in Rm. But we wanted something in Rn. So actually, it must be that these vectors are not in Rm. They must be in Rn. So, okay. And so it must be that actually that's not an M, but an N. And then it must be then that actually this one is the M. There are M of them. Okay. And then it's not clear from this time because 2 and 2 are the same number, but so the way I figure this out is that the results needs to be in Rn, so these vectors need to be in Rn. Okay, and so now the sort of generalization of this theorem is then that x1, a vector in Rn, is sent to a linear combination of those things, and this is why there need to be m of them, because there are m things in here to be scalars, m entries in the vector to be scalars. So it's a linear combination of these things. Oh, that's m, sorry. All the way to x. I mean, that's not an m, that's an n. Jeez. Okay, and then it's traditional to arrange all these vectors as the columns of a matrix. And put this one over here. And then that would be the definition of matrix multiplication for our entire... Yes? So this is just... This thing is just this thing, but instead of having 2 and 2 here, I'm having m and n there. I'm generalizing it. Okay. So I'm asserting without having proven that any linear transformation from Rm to Rn can be represented in terms of, can be written as, instead of saying, okay, it takes x1, it takes this vector and sends it to t of that, I'm saying that actually can be written, what t of that vector is, can be written as a linear combination of certain vectors. In the same way that in this 2x2 case, this transformation could be written as a linear combination of those two vectors. So now, because it's because now it's not 2 entries and 2, because it's not 2 entries here and 2 entries there. The vectors are now bigger. They're like m by n, but it's the same principle. Instead of writing this vector goes to t of that vector, you can say that this vector goes to a linear combination, where the linear combination is the scalars for the linear combination are x1 to xm, and the vectors are these things, and they characterize the linear transformation. Every linear transformation has these vectors, or another way to say it is every linear transformation has this matrix, and that tells you what the linear transformation is. It allows you to say, okay, the linear transformation is just this linear combination. Just want to see how much time there's left. Okay, so, and like I said, I haven't proven this. I've just said it. To prove this, you have to, well, I don't know of any way to prove it other than using bases, and we haven't covered bases yet. So, and proving it is beyond this course. But when we cover bases, then you might want to try to prove it. But what you can do now is prove the other half of this. So I've said that every linear transformation from m to n can be represented by an n by m matrix, right? Now, the opposite theorem is also true. every matrix, every m by n matrix is a linear transformation from Rm to Rn. And that is a thing that you can prove. Again, it's beyond this course, but if you want to, that's a thing you can prove by yourself at this stage. Example of what? Yeah, sure. And I'll revise it as well. Oh, did anyone think of that? Did anyone figure out what that thing is? That's R to the n thing. This thing. Did anyone think about what that is? R to the any integer. So